Another very important concept in thermodynamics is entropy. And in order to talk about entropy, we have to define two important concepts. One is the microstate, and one is the macrostate. So when we talk about a microstate of a system, what are we referring to? It is a particular configuration. So we're going to look at individual constituents forming a particular configuration. Of this for a system. So we're going to talk about this particular configuration as a microstate of the system. For example, if I talk about a gas inside a container, if I specify for you at a certain point in time velocity vector of all molecules in that gas, I would be talking about a microstate of that system. What is a macrostate? It is a description of the system conditions from a macroscopic point of view. And what do we mean by that? For example, if I tell you the pressure of the gas is a macroscopic quantity that I can measure, and it corresponds to several different microstates of the system. Now I want to give you a more concrete example. So the experiment I will consider is tossing a pair of dice. So if you're tossing a pair of dice, as you can see in the picture, for each die you can have numbers between 1 and 6, and I'm looking for the following macrostate. So I would like to have a macrostate of this system. The total is 4. Okay, so how many microstates produce this result? So let's talk about microstates corresponding to this macrostate. Well, the first one can give you a 1, the second one can give you a 3, the first one can give you a 2, second one can give you a 2, the first one can give you a 3, the first one can give you, second one can give you a 1. So you can see there are 3 microstates corresponding to this macrostate. On the other hand, if I say the total is 2, then you must have a microstate of 1, 1, which means just 1 microstate. Then I can ask you how likely it is when you toss a pair of dice the total will be 2. You will probably say that it's not very likely because you have to get 1 on both of them, and the probability of getting on 1 on both of them at the same time will be very low. So this is the basic idea behind entropy. In all natural processes we find that the processes will tend to evolve in a direction that will maximize the number of microstates, which we call entropy. So for all natural processes, there is a preferred direction. They will evolve in a direction that increases the number of possible microstates, and when we have a high number of microstates, we will say the system is disordered. When we have a low number of microstates, we will say it is ordered. So it is degree of disorder we're looking at, and this has to be maximized for the system to likely evolve in that direction. So this degree of disorder, which is related to the number of microstates corresponding to the macrostate we're looking at, is quantified by a state variable called entropy. Now, there is a very important word here, that's state or state variable. So entropy is a state variable because it depends on the state, the macrostate we're looking at, corresponding to how many microstates of the system. So that's basically going to quantify the number of microstates corresponding to a possible state or the degree of disorder, and this will be quantified by this variable called entropy. We show entropy with S. So S is entropy. All right. And the basic finding we have is that if you look at the probabilities of a system evolving in a certain direction, you're going to find out that the probability of a system moving in time from an ordered macrostate, that means low entropy, to a disordered macrostate, many microstates possible, high entropy, is far greater than the reverse. And it has to do with the number of microstates corresponding to the state that it will evolve into. Now, what is the thermodynamic definition of entropy? Basically, I'm going to talk about the connection between number of microstates and this definition for reversible processes in a little while. So first I want to say that entropy change, because it's a state variable, its change is important. Entropy change in a quasi-static reversible process is going to be by small amounts, is ds, is equal to dq reversible divided by the temperature. So we're looking at the heat added to the system in a reversible isothermal process where the temperature is T, and this is going to change the entropy by an amount ds, so that if you calculate the total entropy change in the system from the initial state to the final state, this will be the integral of ds. It will be integral from initial to final state dq reversible divided by T. Okay, so this R stands for reversible. So heat added in a reversible isothermal process, basic. That's dq reversible over T, so that T is constant. So let's talk about the entropy change in the Carnot cycle. So if I look at the Carnot engine, what will be the entropy change? So I have two isothermal processes in the Carnot cycle. So remember, I have isothermal expansion at a temperature TH and isothermal compression at a temperature Tc, and then adiabatic processes have Q is equal to 0, so there will be no contribution to the entropy change. So the total entropy change in the system will be equal to the heat that we are absorbing at high temperature QH over TH plus the heat that we're absorbing, which is minus QC, divided by temperature Tc. So this will be the entropy change of the cycle because there is no contribution from the adiabatic process. This is going to give me delta S, no change in the entropy. Now I know that QH over QC for the Carnot cycle is TH over TC. So the entropy change will be QH over QC 1 over TH minus 1 over Tc multiplied by QC. Alright, so I'm going to have, if I multiply it by QC, I get QH over TH minus QC over TC. So this is going to give me TH over TC times 1 over TH minus 1 over Tc multiplied by QC. So this will give me 1 over Tc minus 1 over Tc multiplied by QC, which is 0. Now, is that surprising? Delta S, the entropy change in a cyclic process, will always be 0. Why? Because it's a state variable. So just like the internal energy change in a cycle is 0, the change in temperature in a cycle is 0, etc. We have the entropy change is 0 in a cycle. So we can show it with this integral here, delta S. For a cyclic process, in order to show a cycle, I put a circle in the integral sign. dq reversible over t is 0. For any reversible cyclic process, because S is a state variable. All right, so that's an important result to remember because it comes from the definition of entropy. It's measuring the number of microstates or the degree of disorder corresponding to a certain macrostate. Now I want to talk about the second law of entropy. Basically, what we said here, all natural processes evolve in a direction that is going to increase the number of microstates, the degree of disorder, or the entropy. This can be summarized as the second law of thermodynamics. So this is another statement of the second law of thermodynamics. Second law of thermodynamics, and we can show that this definition is also equivalent to, or this statement is equivalent to Clausius statement and Kelvin-Planck statements. The entropy of the universe increases in all real processes. So this is another statement of the second law of thermodynamics. If you calculate the entropy change of everything for a process, delta S for the universe, the system and its environment, that's what it means, should be greater than or equal to 0 at least. So it must be evolving in a direction that increases the entropy. Now I want to look at two processes. One is melting of ice. So if I look at this process, melting of ice, so as you know, this is going to happen at a temperature T is fixed. It is the melting point, Tm, melting point. And when ice melts, it's going to absorb heat because the bonds need to break to form water. And for that, I will need the latent heat of fusion. And let's say that I have a total mass m. How much is the entropy change in this process? Delta S is integral dq reversible over T, and the temperature is fixed, so 1 over the melting point, integral dq reversible. So what is the total amount of heat I'm adding to the system? 1 over Tm, latent heat of fusion times delta M, the amount of material that goes through the phase change. This will be equal to latent heat of fusion times the total mass of the ice divided by melting point temperature, because I'm assuming that all the ice is melting. So this process, melting of ice, gives me an entropy change, latent heat of fusion times m divided by Tm. So that's just one example. That basically, what did I calculate? I calculated the entropy change of ice, right? So this is the entropy change of the ice in the melting process. Now another process I want to look at is related to the second law of thermodynamics, the entropy change in thermal conduction. So thermal conduction. So what is the problem here? I have two objects that are connected, that have a thermal contact here at their boundary, and they are isolated from the rest of the universe in their boundaries. I have thermal isolation, except at one point they are connected to one side is connected to a hot reservoir and the other side is connected to a cold reservoir. And when I make the thermal contact at the boundary, here this is a thermal contact, and these two boundaries are thermal insulators, so they're not connected to the ambient. So what am I going to see? I will see heat flow from the hot side to the cold side, and normally this will continue until their temperatures are equal, so that the zeroth law of thermodynamics will take place. But because I have a hot reservoir and cold reservoir that have a very large heat capacity, it's almost impossible to change their temperatures. The temperature is fixed. Then I'm going to expect that a continuous heat flow will occur. In which direction? From hot to cold side. Now let's check if that is consistent with the second law of thermodynamics. So I asked myself, what is the entropy change of the universe in this process? Okay, so what is the entropy change of the cold side? Well, the cold side is absorbing heat plus Q at a temperature, fixed temperature, Tc. And the hot side is providing heat, the same amount of heat Q, at a fixed temperature, Th. They are isolated from the rest of the world, and therefore, well, I can say that this is a hot reservoir in thermal contact with a cold reservoir, basically. So that's part of the system, so there's nothing else to consider here. So these two basically are the same system, and these two the same system. So therefore, I will have delta S of the universe will be equal to Q over Tc minus Q over Th, and here I have thermal insulators, so on the I don't have any heat exchange with the environment in the other boundaries, and therefore this is going to be just this contribution from hot and cold reservoirs, which is Q times 1 over Tc minus 1 over Th. So this is going to give me Q times Th minus Tc over Th Tc. Now, since I have hot side temperature is greater than the cold side temperature, the entropy change of the universe I have calculated here is positive. So second law of thermodynamics applies. Therefore, the second law actually tells me in which direction the heat will flow. It will flow from hot to cold side, because if it were to flow from cold to hot side, the entropy change of the universe would be negative, and the second law wouldn't allow that to happen. And basically, this is one application where we can clearly see the second law is very helpful in telling us in which direction the process will evolve. But as I said, up until now, I didn't form a real connection between the number of microstates and the entropy definition I gave you here for thermodynamic processes. So in the next video, I'm going to consider the entropy change in adiabatic free expansion, and then I will try to calculate the number of microstates, the change in the number of microstates in the system, and find a correlation between this definition and the number of microstates, or the definition of entropy given in terms of the number of microstates.